Hello friends. Up until the last class, we've discussed about what a Nernst equation is, how to use Nernst equation, when a cell is called as standard, when a cell is called as non-standard. And then we did some basic questions also. And then we discussed what are the terms in the Nernst equation mean, what is N, what is Q, and how to find it. Now let's continue that and let's talk about the next part, which is how to write cell, how to represent cell. So we'll discuss about this and then we'll do questions also in the upcoming lectures. So let's start with first what exactly, how is exactly the cell is represented, because if you want to do numericals, you have to understand how a cell is represented basically. So let's begin. Cell representation. So cell representation, there is a theory which was given by IUPAC. IUPAC said that if you want to represent a cell, then we have to do in such a way that just by looking at the representation, the entire picture of the cell should be clear. Meaning, first we will write anode. Then we'll draw two parallel lines like this and we'll separate it with cathode. This is the first thing that IUPAC said. The second thing what IUPAC said was separate two different phases like solid, liquid, solid, aqueous solution by vertical line, by a vertical line like this, and separate same phases by a comma. Separate same phases by comma. We'll use comma to separate the same phases going on. And here we'll write salt bridge. Whatever salt bridge we use, we'll write it here. I'll talk about salt bridge also in upcoming lectures. This is how we can represent a cell. Now, based on this, how we can represent a cell. So let's try to understand with an example. So let's take an example of Daniell cell. Daniell cell. What is Daniell cell? It's an example of galvanic cell. If you remember, I told you that in this case, zinc sulfate is one part and copper sulfate is the other part. And due to these two pairs, we call them as Daniell cell. We call it as Daniell cell. So in Daniell cell, due to the reduction potential of zinc being smaller than the reduction potential of copper, which one undergo reduction? Which one undergoes reduction? And reduction is underwent by copper, and zinc undergoes oxidation. So this undergoes reduction. Hence, where will it happen? At cathode, red cat, right? And this undergoes oxidation. So it will be at anode. Now, so as the rule says, first anode, then cathode. So first let's look at the chemical reaction. So zinc solid is a metal, right? Converts to zinc 2 plus aqueous ion and 2 electrons, right? This is the equation at anode. What is the equation at cathode? So at cathode, the equation is copper 2 plus aqueous reacts with 2 gains 2 electron to become copper solid. So just look at this. Just look at this. What do you see at cathode? What do you see at cathode? Now I'll tell you the cell representation. So at cathode, what do you see first? You see zinc first. So write zinc solid. Then what do you see right just after that? What do you see? You see zinc 2 plus. Which state it is in? It's an aqueous state. So draw a straight line and represent and write Zn 2 plus aqueous. Why one line? Because we are separating two different phases. Then this part anode is finished. This is anode. Then we'll draw a vertical line. I mean a parallel line like this, right? And then what do you see here? You see copper 2 plus first. And then you see coppers. This is aqueous ion, and aqueous, then I represent copper solid. See, this is the cathode. So that's how the particular cell can be represented. And then here you can also write the voltage, whatever it comes out to be. We know it comes out to be 0.76, 0.34 minus 0.76, 1.1 volts. So you can also write 1.1 volt. But this is something usually they ask you to find. So it's okay. This is what you write the cell representation as. So for this particular cell, going, the reactions going on. See, for this particular cell, how do we write the cell representation? Cell representation is written like this. This is how we write cell. First the metal ion, then the so first the metal, then its ion, and then copper 2 plus ion, and then copper. That's how we write it. So this is how cell representation of any cell is carried out. Right? So this is how we can do it. So let me give one question so that you can also practice it. H2, H plus reacting with zinc, giving you zinc, ZnCl2 plus H2. Write cell reaction, cell representation for this. So you can pause the video and solve it. I'll give you 2 minutes time. You can take 2 minutes time, not more than that. Pause the video and please do it. Please pause the video. Okay, so I hope you would have done it now. So let's solve it. So look at the equation. What do you see here? H plus is becoming H2. So plus 1 has become 0. So what is this? Reduction. Right? Reduction. And Zn is becoming Zn2 plus. ZnCl2 means plus 2. And here it is 0. So what can we say? For this part, we can say that it is oxidation. So reduction happens at cathode, red cat. And oxidation happens at anode. Right? Now, we can clearly see that this is the cathode part, this is the anode part. Zinc is solid. This is aqueous because it's in aqueous state. This is gaseous and this is aqueous. Now, so what is the reaction? First we'll add anode. So in anode, what do you see first? We first see zinc. So we'll write zinc solid. This is the cell representation. Cell representation. Zinc, and then we have Zn2 plus aqueous, right? Then this is the end of anode. What next now? Cathode. So we'll separate it by a vertical line. And then we will write H plus ion because that's what we can see here, right? Giving us H2. H2. This is how we can write it down. So that's how the cell can be represented. This is how we can represent a particular cell as per IUPAC. I hope you understood the idea behind how to write, how to do the cell presentation. Now we have to do a small topic, which is standard hydrogen electrode. So we'll be learning about what standard hydrogen electrode is and what is its application. So let's start with that now. So let's begin with that. Yeah, so let's start with the next part, standard hydrogen electrode, and then I'll tell you why it is useful and all these things. What is actually standard hydrogen electrode? So what do you mean by the word standard? I've told you in the last session, standard means temperature 25 degrees Celsius. Very good. Pressure of hydrogen or pressure of the gas 1 atm. Concentration of the ions present 1 molar. That's it, simple. It is the potential of a cell involving a hydrogen atom such that the concentration is unity and temperature is 25. That's it. This is what hydrogen electrode is. Simple, in simple term, this is what hydrogen electrode is. Now let's see how it looks like or how we define it as. So the definition, this is the definition of standard hydrogen electrode. So standard hydrogen electrode consists of a platinum electrode coated with platinum black. Okay, we coat it with platinum black so that it can be made inert. Yeah, it is inert anyway, so we don't have to make them reactive because hydrogen and H plus is the ion. H plus ion and hydrogen gas is the one which comes in contact here. Because see, I told you in the very first lecture what makes potential? What causes potential to appear? Potential comes whenever an ion comes in contact with its atom. Now, sadly, when we had zinc sulfate, when I wanted to have zinc 2 plus ion in contact with zinc rod, I dipped zinc rod in zinc sulfate ion, copper sulfate, copper. But here I cannot have a rod of hydrogen, right? That's the sad part. Can we have a rod of hydrogen gas? Not really. That is why we need a support like platinum black, an inert electrode who can help me to get H plus ion and H2 in contact. If you have been watching my video from the beginning, you would be knowing what I'm talking about. I just also revised it for you that for potential to develop, an ion must come in contact with its atom. And that's possible only in this case because is only possible when we can have hydrogen, coming in contact with H plus ion through some inert electrode, which is platinum. So see, this is how the definition goes like. See, have a look here. So in the definition, as you can see, we have that it consists of a platinum electrode because that's what will be the one which helps in interaction of H plus ion with hydrogen gas. Coated with platinum black. The electrode is dipped in a solution of acid, 1 molar. Why? Because it has to be standard. Yes. And pure hydrogen gas is bubbled through it at 1 atm pressure. You can also say atm, it's fine. You can also use atm. Now, how does it look like? So it looks something like this. I took a container. In the container, I put acid. See, in the container, we put acid. In the container, we put acid. Now the H plus, this is already filled with H plus ion. What's the molarity of H plus ion? 1 molar. Why? Because the cell is standard. Very good. What is this setup actually? This is a setup through which hydrogen gas is coming in, and this is the platinum black. So hydrogen gas comes in here, and then since it is dipped in the solution, H plus ion and H2 gas comes in contact here. And that's how the potential is developed. So why are we using this platinum? Just one purpose, to get H plus and H2 gas in contact to each other. That's the only purpose behind it. So see, this platinum electrode, from there we are giving hydrogen. See what is happening here? As you can see, hydrogen is getting bubbled. As hydrogen bubbles, it gets to spend some time with H plus ion. And as it spends some time, it interacts and develops a potential. It interacts and develops a potential, somewhat like this, see? So it's interacting with it and it's developing a potential, right? So it develops a potential. Next, we'll now see how it is useful. Like, why are we studying all these things? So what you have to write in exam, if this question comes in exam, you need to write basically this definition that you have seen in the previous. This is the definition of standard electrode. Just write this. It will be a 1 mark question. You can easily get the marks. And this is the construction. And that's how it looks like. So basically, how do we represent it? So what all things are actually, seen in this case? So as we can see here, the things that we can see here is a platinum rod, hydrogen gas, and H plus ion. All of these things are actually present. Now it's not a cell, please understand. It's an electrode. This is just one part. The other part would be connected with some other electrode, right? Some other, maybe copper electrode, zinc electrode, whatever. It's just one half of a cell. It's an electrode. In a cell, there are 2 electrodes, cathode and anode. This is just one electrode. It could either be cathode or anode. It depends. It depends on what I'll tell you in the upcoming lecture. So now let's continue this and see the next part. Yeah. So now how do you present the cell? So representation of cell can be done by this way. See, platinum, H2 and H plus ion. That's how we can represent. This is just one half. This is how we represent S.H.E, standard hydrogen electrode. And it has been seen that the E0 value of, it has been seen that E0 value for this would be, I mean, see, you can obviously find the other part, but E0 value of just this reaction, platinum, H2, H plus, is taken as 0 volt. It is not actually 0 volt. It's like taken as 0 volt. It's called as datum or a reference point. Don't get scared of these big terms. This simply means that suppose if there's a race going on, okay, and we say that this is 0 kilometer and this is 1 kilometer. And suppose it's a race of 1 kilometer. Yeah. So is this really 0 kilometer? No, it's a 0 kilometer because I thought that to be 0 kilometer. With respect to this building, it would be 10 kilometers, 20 kilometers, whatever it is. It's not really 0 kilometer. I marked it as 0. This is my reference point. From here, I'm calculating 1 kilometer. Simple. Just like that. So 0 volt is just an idea of making it as a standard. In reality, it may not have a 0 value. We don't know that. Okay. But we assume it to be 0. Right? So since we assume it to be 0, it helps a lot actually. Now, how is it helpful? We'll do this and then we'll wind up with the session. So let me tell you why we study S.H.E. What's the real use of S.H.E.? See, how do you think the values would have come? Imagine you see when you open the book, you'll see some reduction potential values of zinc, reduction potential value of copper, reduction potential value of let's say a silver, reduction potential of all these things are obtained, right? How do we get it actually? Very easy. What we do is on the one side, we take the S.H.E. Suppose this is S.H.E. This is the platinum rod and all this setup. The other side, I pass it through a voltmeter, and the other side we connect it with an electrode, which is unknown metal, right? And we take as standard temperature 25 degrees Celsius, concentration of metal ion is 1 molar. Everything is standard. This is also standard. This is also standard. And then, can you guess what will happen now? Through this, there will be some voltage supply, and suppose the voltage reading came out to be 0.34 volt. Suppose it came out to be 0.34 volt. That is the E0 of cell, because it's now a cell, because we have a cathode and we have anode and cathode, both the things are present. It's a cell now, right? Now let's see how we can use this. What do we know the formula for E0 cell as? E cathode minus E anode. Yeah. So on the left hand side, we always keep anode. So this is anode. And that's cathode. I took S.H.E. as anode on purpose. And this is cathode. Yeah. Now, this is also unknown. This is unknown. Right? Now, E cathode minus E anode. So what is E cathode? We don't know. What is E anode? 0. So what will be the E0 cell? See, E anode is 0. I just told you S.H.E. is 0. So what we have got now, whatever is the E0 cell value, that is the value of E cathode. So see, that is how it is useful. So what I can say ultimately is S.H.E. helps us to find the cell potential of, or reduction potential of what? Of S.H.E. helps us to find the reduction potential of unknown electrolyte. That is why S.H.E. is so important. So now it should be clear why we studied in S.H.E. and what is its application. So this is how we draw S.H.E. See, and that's how the H2 ion and H plus and H2 and H plus is made in contact. And this is the definition of S.H.E. See, this is the definition of S.H.E. S.H.E. definition, diagram. Then we have this representation and the uses of why are we actually studying this. So I hope you understood why we study S.H.E. and what S.H.E. is and how we represent cell as per IUPAC rules. So that's it for in this lecture. In the next lecture, we'll do the thermodynamic treatment of cell and numericals, which is really a very important topic, and we'll practice few questions on that. So I hope this was useful. If you really found this video useful, please share it to a friend, like the video and subscribe my channel. Thank you so much.